All right, let's get started. I opened up the iClicker class so you can join as I go through a few announcements for you all. Let's quiet down. We'll get started with class here. Let's quiet down. We'll get started with class. All right, so the announcements are the same as what you've seen before. Next to Chief homework is due Monday. Midterm is Friday, so there will be about 30 questions. All of them are multiple choice, and we will cover chapters 1 through 4. So we won't get to 5 until next week, so that won't be on the midterm. The learning curves for chapters 3 and 4 are available. They're due at the end of the day on October 20th if you would like the extra credit point, 1 per assignment. So I think it might be helpful to just kind of review what we've covered in all of the chapters. These are the chapter outlines. You have access to all of these slides. But just to kind of go back and jog our memory about what was covered. So chapter 1, the first part of the semester, we talked about what matter is, how we classify matter and different properties of matter. So we talked about physical and chemical properties. We talked about the scientific method and the international system of units, so the standard units that we use to communicate measurements in science. We learned about significant digit rules, dimensional analysis, so converting between different units, density, and then temperature. Chapter 2 is all about the periodic table, so we learned about chemical symbols, the laws of chemical combination. So you might remember if we start with a certain mass of reactants and we do a reaction, same mass of products must be present at the end of the reaction. We talked about a few different experiments that were done in the past to discover what we understand as the atom. So that we have a nucleus with a positive charge, an electron cloud, and electrons have negative charge. So we talked about those experiments. Subatomic particles, so protons, neutrons, and electrons. Isotopes, atoms with the same number of protons but different number of neutrons. And then ions, which are atoms where number of protons is not equal to the number of electrons. Atomic masses we talked about, and the periodic table, that last section was identifying the different parts of the periodic table. So different groupings, alkali metals, alkaline earth, noble gases, halogens, transition metals, all of that was in 2.6. So we took the Unit 1 exam on chapters 1 and 2. So that is a good place to study, to review content from those 2 chapters. So I encourage you to look back at that exam. And then we started chapter 3. So chapter 3 we broke into 2 parts. Part 1 was all about nomenclature. So how do we name all these different types of molecules and compounds? We did binary covalent compounds, ionic compounds. All the polyatomic ions are in that section. So that was the first part of chapter 3. Second part was all about the mole, converting between moles and grams. We have molar mass for individual atoms and molar mass for compounds as well. We determined empirical formulas, molecular formulas, and then did combustion analysis. So there's kind of a lot in chapter 3. And then chapter 4 we're working through right now. So we started with balancing reaction equations. We talked about different types of chemical reactions, how compounds behave in aqueous solutions, and then more specifically precipitation reactions where we form a solid, acid-base reactions where we are showing a reaction between an acid and a base. We are currently working through 4.6 redox reactions and determining oxidation states, and then we'll start 4.7 today and finish it next week. Yeah.
Is there a certain amount of questions from each chapter on the test?
Not necessarily, no. Yeah, it'll be spread out pretty evenly. All right, so I think that's everything really that I wanted to say. When you are studying, so I recommend spending time working on either redoing Achieve assignments or looking at the end of book chapters. There's a section in the ebook in each chapter that has end of chapter questions. So those are a bunch of questions that you likely haven't seen before. And then within Achieve, if you navigate through course content folders, you can find the answers to odd end of chapter questions. So you can try out some questions and see if you're getting the right answer. So I think that doing practice problems is going to be helpful because that's what the assessment is a bunch of practice problems. So that is a good way to see what knowledge you have and if you can apply it to a practice problem. If you're struggling with some problems, then you know you should go back to the PowerPoint and maybe review that content. There's also the learning checks within the PowerPoints. Those are good to retry. So try them without seeing the answer. Maybe try without your notes since you won't have your notes when you take the exam, and then see how you do, what you need to improve on by comparing to the answer. There are the learning curves, which is a good review for chapters 3 and 4. I think that might be everything. iClickers. So yeah, lots of resources, and I still have my office hours, and we have recitation next Wednesday, so we can talk about any of that content during that time as well. Any questions about what's coming up? Yep. No.
For the multiple choice, is there going to be like partial credit, or is it like if you get it wrong?
It's, yeah, just right or wrong for multiple choice. All right, so at the end of class on Wednesday, we started talking about oxidation reduction reactions, determining oxidation states. This is another oxidation reduction reaction. There's a little bit of background information we'll talk about. Really, we're focusing on the reaction equation that's stated here, but in the statement, it says magnesium metal reacts with HCl, generating H2 gas and a solution containing magnesium 2+ cations. Now you see HCl is stated and then H3O+ in parentheses. So this happens a lot in chemistry. Just giving you some background here, but again, we're just going to focus on that equation that's written there. But when you add HCl to a solution, so HCl plus water, well, HCl is one of our strong acids. So HCl will donate a proton to water, and we end up with H3O+ and Cl- anions. The H3O+ is then what is going to react with magnesium. So that's why we've only included H3O+ in that reaction equation. That's not something I'll ask you to do on the assessment without a lot of guidance. So just wanted to give you that background. The Cl- ion comes up in this table. That's where it comes from. Now, if we're looking at that reaction equation that was provided for us, we know it's stated that this is a redox reaction, so we can determine oxidation states of different atoms. So let's do that, kind of reviewing our rules. We have magnesium as a solid. That's an individual element on its own, not in a compound, doesn't have a charge, so its oxidation state is 0. In H3O+, we have hydrogen and oxygen. Oxygen typically has an oxidation state of -2. Hydrogen typically has an oxidation state of +1. We need to check to make sure that fits with the molecule that's represented here. We have H3O+. This molecule does have a charge, so the sum of all oxidation states should be +1. We have 3 hydrogens with a +1 oxidation state, so +3 total. We have 1 oxygen with a -2, +3, -2. We have +1 overall. So that works for this compound. Okay, so we've taken care of all elements that are reactants. Now we look to the products. Magnesium 2+, that is a monoatomic ion. According to our rules, monoatomic ion oxidation state is the same as the charge. So its oxidation state is 2+. Hydrogen gas, H2, that is a single element on its own, not in a compound with another element. So hydrogen in H2 has an oxidation state of 0. H2O, we follow our -2 for oxygen, +1 for hydrogen. So all of the rules that I followed are the rules we discussed in class on Wednesday. Once we have oxidation states for all atoms in reactants, all atoms in the products, we can compare to identify what is oxidized and what is reduced. This table summarizes what's going on here. So we start with magnesium, solid, oxidation state of 0 as a reactant, and we get magnesium 2+ as a product. H3O+ forms H2 gas. Now you see we also have H2O as a product. We still do have H2O as a solvent as well. So this goes into that background information that you don't need to worry too much about, but this is where that's originating from. We have water and we add some HCl to the solution, and we get some H3O+, but we also have some H2O liquid left over. Usually when you're adding an acid, you have a lot of water and you're adding a little bit of acid. So not every water molecule is converted to H3O+. All right, so we have H2O solvent, and then chlorine chloride ion is our spectator. It's not involved in that redox reaction. So now moving on to the next slide, we see magnesium starts at magnesium 0, goes to magnesium 2+. It has increased in oxidation state, meaning it has lost electrons. So it lost negative charge, increased in oxidation state. It is what is oxidized. And then H3O+, the hydrogen in H3O+, became H2 gas. Hydrogen with a +1 oxidation state as a product has a 0 oxidation state. It decreased in oxidation state, so it was reduced by gaining an electron. So we have a full reaction equation here, but we can separate the oxidation, the atom that's oxidized, and the reduction, the atom that's reduced, into what we call half reactions. So that's what we'll do on this next slide here. To balance a redox reaction, we separate the oxidation half reaction from the reduction half reaction. And we'll talk about what that half reaction is. Once you have the oxidation half reaction and the reduction half reaction, we need to verify that numbers of electrons transferred, so electrons lost in the oxidation and electrons gained in the reduction, are equal. Now we can find the total net reaction by adding the two reactions together, the two half reactions. So let's look at this oxidation half reaction first. It's a half reaction because all that is included here is what is oxidized and the electrons that are lost. So we started with magnesium solid. We go to magnesium +2. The magnesium metal lost 2 electrons, so we include the electrons as a product. For the reduction, we started with hydrogens and H3O+, and hydrogens were reduced to H2 gas. We have 2 hydrogens that are reduced to an oxidation state of 0. So 2 hydrogens that had a +1 oxidation state now have a 0 oxidation state. Each of the 2 hydrogens gained 1 electron, so we have 2 electrons. 2 electrons are getting, or 2 atoms are getting reduced by 1 electron each. In this case, number of electrons gained in the reduction is equal to number of electrons lost in the oxidation, so we can add everything together and we get the net equation. We'll do an example maybe on the next slide where they're not equal. We'll have to use some factor to multiply all of the coefficients to get number of electrons reduced or lost equal to the number of electrons gained in the 2 reactions. But this is the idea for half reactions, oxidation half reaction, and reduction half reaction. So let's do 2 more examples. We'll do the first one together, and then I'll have you all try the second one on your own. We're looking for substance oxidized and substance reduced in each of these reactions. Whenever you see a metal on its own as a solid, you can go ahead and say that oxidation state is 0. Next we have HCl. H usually has a +1 oxidation state. There is no charge for HCl, so the total oxidation states for the 2 atoms, hydrogen and chlorine, should equal 0. So if hydrogen is +1, chlorine is -1. In magnesium chloride, now we have a binary ionic compound. We can assume the oxidation state of the nonmetal, so chlorine in this case, is equal to its ionic charge. So chlorine has a -1 ionic charge. We know that from the periodic table. When it's in a binary ionic compound, we can say that its oxidation state is the same, so -1. We have 2 chlorines with the oxidation state of -1. We have 1 magnesium. We need the sum of oxidation states to be 0. So we have a +2 oxidation state for magnesium. And then hydrogen, excuse me, hydrogen as a gas on its own, not bonded to anything else, has an oxidation state of 0. With this, never mind, hold on, there's a question, go ahead. Not when it's not bonded to anything else. So we only have hydrogens here. When you only have hydrogens, H2 gas, you have oxidation state of 0. This is how hydrogen exists in its elemental form. It doesn't exist on its own, it's just 1 hydrogen. So that will have oxidation state of 0. When hydrogen is in a compound with some other element, its oxidation state is usually +1. Okay, so with all of that, tell the person next to you what atom is oxidized, what atom is reduced. All right, what is oxidized? Magnesium. How do we know magnesium is oxidized? It increases. Its oxidation state increases. It becomes more positive. That means it lost electrons. Electrons are negatively charged. It lost electrons. So it is oxidized. So magnesium is oxidized. What are we so confused about?
If you add, if oxidation state is like +2, it's losing electrons?
Mm-hmm. I know. It's confusing because it's like there's more. 2 is greater than 0. So the oxidation state increases, but the key is remembering that electrons, we're talking about loss or gain of electrons, and electrons are negatively charged. So if you gain electrons, your oxidation state decreases because you're gaining more negative charge. If you lose electrons, you become more positive, and that's oxidation. Yes. Did magnesium gain electrons? It lost electrons. Its oxidation state increases because it lost electrons. The oxidation state becomes more positive because it lost ownership of negatively charged electrons. Yeah, no problem. I understand this can be counterintuitive, but remembering electrons are negative, I think, is key. So magnesium is oxidized. That means what's reduced? Hydrogen is reduced, so it starts at a oxidation state of +1. It is reduced to 0, so hydrogen is reduced. Now we can write the oxidation half reactions and the reduction half reaction by including the individual atoms that are oxidized. So we have magnesium starts with a oxidation state of 0. So we're going to now write the half reaction. We'll just start with magnesium. Starts with an oxidation state of 0, and it turns into magnesium with an oxidation state of +2. And that means that it lost 2 electrons. So we add our 2 electrons lost right there. Hydrogen starts with an oxidation state of +1. It gains 1 electron. And we end with an oxidation state of 0 for hydrogen. Okay, try out the next one. Identify what's oxidized and reduced. So you have to identify oxidation states and then look for change in oxidation states. Good question. Oh, very true. Yeah, I just wrote So just so everyone knows, sometimes, and I'll be more consistent. Sometimes when I'm representing an electron, I'll circle the negative charge. I didn't for the first half reaction, but I did for the second. But I'll continue circling them. That's just to represent an electron that has If it's just one atom without a charge. So you'll see like H2, Br2, Cl2, F2, O2, all around if there's no 2 for any of those atoms, they will have hydrogen charge, and then the atom
So this one's 0. Yeah, that's one.
All right, let's start going through this one together. So we have aluminum solid, another solid metal not bonded to anything else, oxidation state of 0. We have Br2 as a liquid. This is very similar to H2. It is one element not bonded to any other element. This is the elemental form of bromine. It has an oxidation state of 0. So any diatomic, Br2, Cl2, F2, H2, O2, N2, all of those will have an oxidation state of 0. In the product, we have another binary ionic compound, so an ionic compound with 2 different elements. When we have a binary ionic compound, we assume that the charge of the nonmetal is the oxidation state of the nonmetal. So bromine is in the 7th column of the periodic table, typically has a charge of -1. We have 3 bromines with an oxidation state of -1, so we have 1 aluminum that must have an oxidation state of +3. I believe for all binary ionic compounds, the charges of those ions will be the same as the oxidation state of the ions. We're going through the same process to determine oxidation states as we would for charges. Okay, so what is oxidized? Aluminum, yes, aluminum with an exclamation point. Aluminum is oxidized. It starts with an oxidation state of 0, ends with +3. It increased in oxidation state, meaning it lost electrons. So aluminum with an oxidation state of 0 is oxidized to aluminum with an oxidation state of 3+, and it lost 3 electrons. Oxidation reactions, you always have electrons on the product side because that is being lost. For reduction reactions, electrons are on the reactant side because they are being gained by the reactant. So aluminum is oxidized, bromine is reduced. So bromine starts with an oxidation state of 0. It gains 1 electron, and we have bromine, forgot to specify electron, with a -1 oxidation state. Yes.
Do we not care about like any of the coefficients?
Yeah, great question. So when we're just writing the oxidation half or reduction half reactions, we don't care about coefficients. When we balance them by balancing number of electrons gained is equal to number of electrons lost, then the coefficients that we get in our net reaction should have the whole equation balanced out, and we would get the same as what's up here. So let's go to, let me think of how I want to do this. Okay, here's what we're going to do. So I want to balance this second reaction here. When we're balancing reactions, you'll notice that aluminum, we kept on its own as a solid. Bromine is in the Br2 molecule. We wrote it as just the element. In the products, we have aluminum bromide as an aqueous molecule. We have aluminum as an aqueous ion and bromine as an aqueous ion. So all of this is fine when we're balancing, except for the Br2, or the bromine that we separated into Br2. So this should remain as Br2. Because it is not an aqueous molecule, aqueous ion, we can't separate it into its ions. It will remain as that full compound. Aluminum doesn't have a subscript here, so we keep aluminum 0. And then aluminum 3+ is aqueous, Br- is aqueous. So all that is fine and dandy. But now with Br2, we don't have a balanced equation here. We have 2 bromines on this side, each with an oxidation state of 0. 1 bromine over here. We need to balance bromines. So we have 2 bromines here. And then we need to also have 2 electrons, since now we have 2 bromine atoms. Each one gains 1 electron, so that's 2 electrons gained total. Okay, so now we've taken into account everything that we need to for the half reactions. To balance them, we need to have the same number of electrons lost as the number of electrons gained. So we need to use a coefficient now to multiply each reaction, different coefficient per reaction, to have electrons lost equal electrons gained. We have 3 electrons lost in the oxidation reaction, 2 electrons gained in the reduction reaction. So to have the same number of electrons lost as the electrons gained, we need to multiply oxidation reaction, half reaction by 2 to get 6 electrons lost. Multiply reduction half reaction by 3 to get 6 electrons gained. So multiply by 2 to balance electrons. And here we are multiplying by 3 to balance electrons. To save space, I'm just going to add or input all of these coefficients now. So we're multiplying each coefficient by 2. So we'll have 2 aluminum, 2 Al3 plus, 6 electrons. And then for our reduction reaction, we're multiplying each coefficient by a factor of 3. So 3 Br2, 6 electrons, 6 Br minus. Now that we have the same number of electrons lost as the number of electrons gained, we can write the net reaction where we cancel out anything that's present in both reactant and the product side. When you do a redox reaction, that should always be the number of electrons. So we have 6 electrons as a product on the oxidation half reaction, 6 electrons as a reactant in the reduction half reaction. So those are canceled out, and our net reaction is 2 aluminum, oxidation state of 0, plus 3 bromine, Br2 with the oxidation state of 0, and we get 2 aluminum, 3 plus, and 6 Br minus. Yes. Because we needed to have, well, there's, are you asking about the second one?
Yeah.
Yeah. So we start with Br2, so we should have 2 Br minus to balance the number of atoms. So that would be 2 electrons. And then we need to multiply by a factor of 3 to balance electrons. You're welcome. Okay, now if we go back to the original equation that's given to us, we have 2 aluminums, 3 bromine, Br2s, 2 aluminum, 3 plus cations from the aqueous compound, and then a total of 6 Br minus anions from the aqueous compound. So we have 3 and then a coefficient of 2. I believe on active, when you're putting the net reaction together, if you have an aqueous compound, these should be combined into the aqueous version. So what's provided above, where you have 2 Al Br3 aqueous. Yep, go ahead. Yeah, and then on active, you should include the states as well. I'm a chief, sorry. I was active in my other class. What'd you say? It will say to include the states, or it will be a multiple choice question and the states will be already in the answer. All right. Another question for you all. This one is an iClicker. But what we're going to do here is ignore the second part of the question. So don't write the oxidation half reaction or reduction half reaction. It's more complicated than we need to get in our class this semester. We're going to come back to oxidation and redox reactions in Gen Chem 2. So don't do the last part. goal here is to determine what is oxidized, what is reduced, what's the oxidizing agent, what's the reducing agent. You have 3 questions, which is what's oxidized, what's reduced, and what's the oxidizing agent. 2 things you need to know before you get started. In hydrogen peroxide, H2O2, so the second reagent that's listed here, oxygen doesn't have its typical -2 oxidation state. This is something I'm telling you right now, and I would tell you if this were a question because this doesn't follow our pattern, so don't worry about remembering this. But in hydrogen peroxide, oxygen doesn't have the -2 oxidation state, but hydrogen does have +1. So you can assume that the hydrogen oxidation state is +1. For lead sulfate, we can assume lead has an oxidation state of +2. So use that information to complete the question. Then we'll go over this together.
Yeah. But how do you go with three? All those four. Yeah.
The compound, so the compound that provides electrons for something else. I think that was
Yeah, it's backwards. I think I think the oxidizing agent is whatever doesn't have.
Okay, let me go back. I know this is you guys.
No, actually, I lose
The species that has the alkyl that is reduced is the oxidizing agent. So which one's being reduced? Oxygen. So H2O2 is the oxidizing. Whatever. All this.
Two more minutes?
Don't worry about it. Because it's backwards.
Yeah, but, okay, so the reduced for any reaction.
Assume that whatever doesn't make sense. If it seems wrong, it's
Something else.
Yeah, so that's why the
So are we?
Why? So I know.
Okay, so it says lead is So that would be plus two for the
So the oxygen, this one was oxidized, the oxidized.
Okay, I'm gonna do one more minute. I know it's rushing some of you, but I want to talk about two more slides before the end of class because you need it for your achieve. So try to get at least one, maybe two answered if you don't have them yet, and submit them. Do 10-ish more seconds. Try to get something in. All right, 5 seconds here. All right. Ending it. Okay, I was definitely expecting a mix here. So this is a more complicated question for identifying oxidation states. First one is a binary ionic compound. We use the charge of the anion, sulfur, -2 oxidation state. So lead is +2. In hydrogen peroxide, we have 2 hydrogens, 2 oxygens. I told you hydrogen is +1, so oxygen must be -1 to get neutral overall. In lead sulfate, oxygen is -2, so that's a total of -8 because there are 4 oxygens. We have +2 from lead. To get neutral overall, the sulfur must be +6. In H2O, we have +1 for hydrogen, -2 for oxygen. That follows the normal states. So then sulfur goes from -2 oxidation state to +6. So sulfur is oxidized. Oxygen has a -1 oxidation state and then becomes -2. So oxygen is reduced. The oxidizing agent is the compound that contains the element reduced. So the oxidizing agent is the compound that takes electrons away from something else and gains electrons. It causes something else to be oxidized. So in this case, the oxidation agent, if oxygen is reduced, the oxidizing agent is H2O2, hydrogen peroxide. It takes electrons away from the sulfur, causing the sulfur to be oxidized. So the reducing agent is then lead sulfide. Okay, 3 quick slides before we're done. I'm going to be as quick as I can. This one's not in your PowerPoint, so just look up here really quick. This is in the book, so you can look in the book. Everything that's on here is in the book. But the point of this slide is that if we have copper sulfate in solution, copper +2 charge, and we add zinc, zinc will give electrons, so we have a redox reaction happening. Zinc will give electrons to the copper because zinc is more reactive in its metallic form than copper is. And we get zinc with a +2 charge and copper as a metal. If you had zinc with a +2 charge in solution and added copper metal to solution, no reaction happens because copper is not more reactive than zinc. So some metals are more reactive than others, and that's why we have a metal activity series that will tell us which metals will displace others. So a metal ion in solution can be displaced by another metal ion, depending on what those metals are. So some metals are easier to oxidize, to lose electrons. Some are more difficult. Some are easier to reduce, gain electrons. Others are more difficult. So the metal activity series helps predict the likelihood of these various metals taking part in chemical reactions. And a quick look at this metal activity series. There are more details in the book, but this summarizes as much as we need. The cations on the top of the series are more difficult to displace. So once they are ions in solution, they will stay ions in solution. These ions are easy to displace. So if you have a gold cation in solution and you add potassium metal, potassium will give electrons to gold and produce neutral gold solid, and we have potassium cations in solution. So those metals on the neutral side are easily oxidized to the plus, the cation version. These cations are easily reduced to the metal neutral version. Yeah.
Are we going to have to memorize a few of these?
There's one easy pattern to remember. All of the elements at the top are to the left side of the periodic table. Everything down here is to the right. So if you're comparing anything, it will be very obvious. One's on the left side, one's on the right side. We'll talk about that more on Monday.
This is I got 3 out of 3. I think I remember putting lead for the first one, and you said it was the sulfur. So I don't know.
Oh,
And then it has that.
okay. That's good to know. I will check. Yeah. Yeah, we didn't get to that one, but yeah, I will check the grade book. Thank you.
On the test, we got like the polyatomic ions and like the charges for
You have to remember those. So that was in an announcement to remember most of them that are in the PowerPoint.
Okay.
Yeah, I know it's a lot, but they come up a lot in chemistry, so yeah.